right, good morning. I was really tired this morning when I woke up, so I decided to have perhaps unwisely, to have a mocha this morning. And so I kind of got a good little caffeine buzz going here. We'll see how it affects my teaching. See how crazy I end up being today. We've got three main things to do. Here in class number 26, again, I think we have about 40 classes for this semester here. So we're getting close to the end here, almost into the last quarter. I want to do one more example with the trace-determinant plane. Actually a pretty complicated example, but I want to show you what you can do in a kind of complicated example and use technology. I did decide that I am going to want you to be able to solve a three-dimensional system with help, and I'll talk about what kind of help I can give you. And finally, we'll talk more about forced harmonic oscillators. That's the main topic for today. All right, let's come to the trace-determinant plane example. We're calling this a complicated bifurcation problem. So my matrix, you can see here, involves a couple trig functions of A, little a. Capital A, the matrix, has entries cos 3A, sine 5A, -1 and 0. Okay, don't forget what we're talking about here. We are talking about the corresponding system of differential equations written in matrix form like that. Now, little a is a parameter. We're interested in knowing what happens as little a varies. The trace of this, as a function of a, is cos 3a plus 0, cos 3a, and the determinant is 0 minus -1 times that, which will be plus sine 5a. And if you've taken multivariable calculus from me, you maybe remember if you graph that kind of thing as a parametric curve with parametric plot, it's pretty interesting looking. It's even got a name. Does anybody remember what the name of this curve is? It starts with an L. Talked about it in multivariable calculus, and I know many of you had that with me. It was sort of a French sounding name. Lissajou? Remember that? You don't remember that? Lissajou. Sort of French looking. I'm not sure if it's French. Lissajou figure. Yikes. Or cool. All right, let's manipulate it. Make the right endpoint of the interval of the plot b, and let b vary from just barely bigger than 0 up to 2 pi. Better fix a plot range here. There we go. There's my parametric curve. What is that? Is that a solution curve? Yes or no? Is that a solution curve of the system? What am I doing? It's crossing itself. It's an autonomous equation. It can't cross itself. It's not a solution. It's just the parametric curve defined by these equations in the trace-determinant plane. Probably wouldn't be good to label the axes. The touchdown plane, TD. You're just keeping track of the trace-determinant. That's all you're doing. It's going to cross the critical loci a lot, isn't it? There's going to be lots of bifurcations. Let's add the critical loci in here. Show let's see, I have a parametric plot right here. Add in a plot of t squared over 4, that's the repeated root parabola. Oh, we gotta fix the origin. Really annoys me when Mathematica chooses to do that. Axes origin. There's the repeated root parabola. Anytime that trace-determinant curve crosses that repeated root parabola, there's a bifurcation. If we're analysts, not topologists, we are going to be analysts, it's going to be a bifurcation from spiraling to non-spiraling. You can put the t-axis in here. It's the graph of d equals 0, right? The determinant of 0 is when you're on the t-axis. It is making it extra boldface there. You're going to have bifurcations every time you cross that, too. And then the positive d-axis, how can I get that in there? Let's see, contour plot maybe? Contour plot. Can plot equations. T equals 0 is the d-axis. And if I want the positive d-axis, I let d be greater than 0. I think there will not be a problem with capital D being the reserved thing for the derivative in Mathematica, because I'm putting it in here as a variable. I think this will be okay. Yep, graph the positive d-axis. So there's lots of bifurcations. Oops, something's goofy. There. Something's wrong. Okay, well, every time it crosses the positive d-axis, there's a bifurcation as well. How could you find the bifurcation values? Well, I won't try to find all of them. I'll try to find the most complicated ones when it crosses the repeated root parabola. What you can do to help yourself understand what values of A is the parameter, what values of A lead to bifurcations, is to graph, instead of in the parametric TD plane, graph T and D as functions of A individually. Actually, that's not quite right. Graph, let's see, T is cos 3A. Graph T squared, or maybe 1/4 T squared. Let's do it that way. And D individually. In a regular plot, this is plot, regular plot, as functions of A. Why am I doing this? What do you think?
Is it supposed to be sine phi?
Yes, thanks. Why do you think I'm doing this? I'm plotting T squared over 4 and D as functions of A. Got a guess as to why I want to do that?
Whatever values of A that the two plots will intersect will be a value that is on the line.
Exactly. Yeah, in the TD plane, you got the repeated root parabola, D equals T squared over 4. Anytime your curve, your parametric curve here, crosses that, is going to be a value of A where these graphs, these regular graphs, happen to cross. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crossings on this interval, corresponding to 10 crossings of the repeated root parabola here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the second plot helps us see approximately what values of A that occurs, and if we want to find more closely what values of A, we can maybe use nsolve or find root. Let's see what nsolve does. We may not find all the solutions. When are these functions of A equal to each other? It's going to find some of the solutions at least. I'm not sure how many. Okay. Let's try find root instead. find them one at a time. Find root will find solutions, but we have to give guesses. Let's pick the one that's close to 2 there. Let's give an initial guess of 2. 1.85631, right about there. That value of A is going to correspond in the TD plane to a repeated root parabola crossing. So for us as analysts, that's going to be a bifurcation from spiraling to non-spiraling, or vice versa, as A increases through that value right there, 1.85631, approximately. Okay?
Find root. So did you give it an interval, say from 0 to 2 pi?
I never tried that. I'm skeptical that it's going to work, but let's see. Okay, it's picking something for A in particular, not a bunch of things in the interval. Okay? So with technology's help, we can do complicated problems like this. And this is a good method. All right, what should you know about three-dimensional systems and finding general solutions and particular solutions of IVPs? Well, here I have a very complicated 3x3 matrix. Why I picked such a complicated one? Well, I was trying to come up with an example actually where the eigenvalues were simple. It doesn't look like they're going to be simple here, but they are. The eigenvalues are simple, -3, -2, 1. The eigenvectors are not so simple. On a test, if I give you a problem related to a 3x3 system with this particular 3x3 matrix, I would give you the eigenvalues. I wouldn't expect you to find them. And I would also give you the corresponding eigenvectors. I wouldn't expect you to find that. You couldn't find them unless you knew how to calculate determinants of 3x3 matrices, and some of you probably do, but it would be a pain, and you'd get a cubic characteristic polynomial that you'd have to try to find the roots of. If you graphed it, you could, but it would be a real long, painful problem. So I'd have to give you those things. What should you know how to do with those things? You should know how to write down a general solution from these. Take it one by one. The first eigenvalue here, -3, has eigenvector -1/3, 1/2, 1. So you can write the first term in the general solution like this. It would also be okay to multiply this vector by 6 to get rid of the fractions. And if you did so, you'd have a -2, 3, 6. That would be okay. General solutions are not unique. Solutions of IVPs are unique, but general solutions are not. Next eigenvalue is -2. Corresponding eigenvector, 2, 5/2, 1. Next eigenvector is, or eigenvalue is +1. Corresponding eigenvector, I forgot my K3 here. Corresponding eigenvector, -1/9, 4/9, 1 here. I am implicitly assuming something in writing this down. I am assuming these three eigenvectors are linearly independent as a set. I haven't really said what linear independence means for three vectors. Suffice it to say that they are linearly independent, and that will definitely happen as long as your eigenvalues are distinct, and sometimes even when they're not distinct, sometimes when they're repeated, although that's kind of rare. Definitely when your eigenvalues are distinct, -3, -2, and +1 in this case, turns out to be a fact from linear algebra that the corresponding eigenvectors as a set are linearly independent, which is going to allow you to say this is a general solution. This will allow you to solve any initial value problem. If I give you a particular initial value problem, y of 0 equals y sub 0 equals 7, 5, -4, theoretically you should be able to solve this for the unique solution. Find k1, k2, and k3 such that when t is 0 you get that. It's going to be a system of 3 equations and 3 unknowns, k1, k2, and k3, that will be solvable. Be kind of a pain. You'd have to, if you're in linear algebra, you know you can use elimination. I'd have to give you a simple example probably, where some of these entries are 0 to make it not too painful to solve, since we haven't talked about solving 3x3 systems. Okay? I'll probably try to give you a practice problem or two where things are relatively simple, and again, I give you the eigenvalues and the eigenvectors. And hopefully it's relatively simple to solve for K1, K2, and K3 if I give you a problem like this on the test. Okay? Again, I'll give you some practice problems. All right, that's the main thing I do want you to know how to be able to do from section 3.8. It is worth reading the section if you haven't. All right, the main thing to focus on now is forced harmonic oscillators. We considered exponential forcing the other day, last Friday. Today we're going to consider sinusoidal forcing, where your forcing function on the right-hand side is a general sinusoid, meaning a linear combination of cosine and sine, say of the same frequency. We're using the same coefficient of t here. Theoretically, I could use different coefficients of t, but I'm not. And in fact, we're going to simplify it more. Let's consider these two special cases. Let's get rid of the sine and only consider a cosine forcing function on the right-hand side. There and there. This one, you can see, has no y prime term. That would be an undamped harmonic oscillator, no friction. By putting a py prime in there, that's damped. There is friction there. I could allow some arbitrary amplitude in front of this forcing function. I'm not going to keep things as simple as possible. We will allow an arbitrary coefficient of the t and omega. 2 pi over omega would be the period of the forcing, right? You take 2 pi over the coefficient of t to get the period, the amount of time between peaks in the forcing function, maxima. Its reciprocal, omega over 2 pi, would be the frequency, and if time was in seconds, the frequency would be in hertz. Omega itself is sometimes called the angular frequency. We'll talk about what that means probably on Wednesday. At the moment, that's just what we call it. Omega is the angular frequency. Let's go ahead and consider this unforced case. That's the simplest case first. Some pretty interesting things can happen in this kind of situation. What's a realistic situation where you might need this model? I mentioned this last Friday. If you had a mass on a spring sliding back and forth on an icy table inside of a vacuum chamber with, no friction in the spring, and you move the table up and down. Got a harmonic oscillator in my water there. Move the table up and down like this in a periodic way. That would be something where something like this would be a valid model situation. I'm going to do the general case here for an arbitrary q and an arbitrary omega. And it is supposed to be omega, not a w. When you become a mathematician, that's always omega. Or if you become a physicist, or an engineer even, chemist. I always used to make my w's like that. Now as a mathematician, I make my w's like that, because that's omega. Okay? So don't say w, say omega. I won't get mad at you if you say w, but try to make a habit of calling that omega. More stories. I always used to make my 2's like this, but now I make my 2's like that. I don't know why I started doing that, but I always used to make my z's like this, but once you become a mathematician, you make your z's like that. Because if you make your z's like this, it can look like a 2. Anyway, in case you were ever wondering. All right, let's consider this. It's nonhomogeneous. That's going to be synonymous now in chapter 4 with forced. You can think of it as a forcing function. You can think of y double prime as being acceleration. If you had a 0 over there, it would be a basic harmonic oscillator with no damping. And the force would only come from Hooke's law. But we got this extra force, this external force on here. This is a forced harmonic oscillator. However, you can consider the associated homogeneous equation unforced. So non-homogeneous is going to be forced here in chapter 4. Corresponding homogeneous equation is going to be unforced. Start getting used to that terminology. Y double prime plus QY equals 0. You should be able to write down the general solution of this kind of equation super quick. You don't have to go to vectors and matrices. You just guess e to the st, y equals e to the st. You're going to get the characteristic polynomial to be this. And that would be the same thing you'd get if you use the matrix approach. I guess the polynomial is that part. Right? We've done this before. Coefficient of y double prime is 1, so the coefficient of s squared is 1. There is no y prime term, so there's no s term down here. The constant term is q because that's the coefficient of y up here. Setting this equal to 0 and solving for s gives the eigenvalues, which in this case are purely imaginary, right? S squared equals negative q. Q is a positive number, so negative q is negative. The eigenvalues, whether you want to label them s or lambda, doesn't matter, are going to be plus or minus I square root of q. Euler's formula gives us a complex solution that looks like that. Well, okay, that's a complex solution. Euler's formula allows us to think of that complex solution like this. And that's going to mean your corresponding general solution of the associated homogeneous equation, the unforced equation, is a linear combination of the real part and the imaginary part. YH is going to be K1 cos square root of QT plus K2 sine square root of QT. This thing here is a complex valued solution. And the key fact about it is if you take the real part and the imaginary part, the real part doesn't have an I next to it, the imaginary part does, and form a general linear combination, that's the general solution, or a general solution of the unforced equation here. All right, but then we also want to find a particular solution, a YP. Actually, let me call it, I'm going to call it YC. But I'm going to write down a different equation first. We want to find a particular solution to this equation, a YP. You certainly could write YP equals A times cosine omega t plus B times sine omega t as your guess. And that would certainly be fine. But we're going to use complex numbers more. Partially because it's fun, partially because it's cool, partially because there are other benefits to it. We are going to complexify, I'm not even sure that's a word, complexify the original equation. This is the associated homogeneous equation for the original non-homogeneous equation. We're going to consider a complexified equation where instead of having a cosine on the right-hand side, we're going to have an e to the I times omega t. We're going to consider that non-homogeneous equation, where the right-hand side is a complex valued function of t. Why are we doing this? It's fun. It'll give us some insights and some tricks to do some pretty cool things. Okay? In a nutshell, that's the reason. Partially because it is fun. I think it's fun. It does give you some insights, though. We will see. There are good reasons to do it. We're going to guess a particular solution of this thing. yc we're going to call it instead of yp. C to emphasize that's a complexified equation. It's going to turn out, because this is a cosine here, that the real part of yc will be a particular solution of yp of this thing. If this had been a sine, we'd take the imaginary part. This is all in the reading too. We're going to guess. Hey, instead of guessing a trig function, this complexified equation has a forcing function that's exponential. We can guess an exponential. How about some constant a times e to the I omega t? Its derivative by the chain rule will be I omega a e to the I omega t. And its second derivative by the chain rule again gives you negative omega squared a e to the I omega t, right? Because I squared is negative 1. Right? You can nod. It's not clear where this is leading us. Just for the moment, we're having fun. Plug it in and see if you can solve for a. An a that makes it work. Substitute into the left-hand side yc double prime plus qyc is going to give you, there's yc double prime, there's yc, multiply that one by q. Both of those two things have a factor of a and a factor of e to the I omega t, which can be factored out. I'm going to factor it out like this. I'm going to put the a first, put the e to the I omega t over here. I'm going to have a q from this one because of the q there, minus omega squared. Take a second to look that over, think about it. When I plug yc into this left-hand side, yc double prime is this, plus q times this. Both of those have a e to the I omega t as factors that can be factored out. What's left over? Q from this one, because of the q there, and a minus omega squared from this one. I want to set that equal to this thing and see if I can solve for little a. And I can. Little a times this will have to equal the coefficient of this, which is 1. So little a will be 1 divided by q minus omega squared. Although I guess I want to avoid one case, don't I? Two cases. Actually, q is positive, and we can think of omega as positive. I don't want q to equal omega squared. Equivalently, I don't want omega to be plus or minus square root of q. I could just write plus square root of q since we're going to typically consider omega to be positive. Evidently, that's a special case where this doesn't work. Okay, so we are not in one of those cases here. Okay, what's the punchline? Where are we here? So I found a value of a that's going to make this function be a complex solution of this complexified equation. The real part of yc will be a particular solution of yp for the original forced and non-complexified equation, which should make intuitive sense by now, but that's the case. Since the right-hand side of the original equation is cos omega t, I take the real part of yc as my yp. If this had been a sine omega t, by Euler's formula, I would take the imaginary part of yc to get the yp. This is the real part. RE stands for real part of 1 over q minus omega squared e to the I omega t. I put the omega t in parentheses to emphasize that's what goes inside the cosine and the sine. By Euler's formula, this is cos omega t plus I sine omega t. 1 over q minus omega squared is real. So the real part of this product is going to involve 1 over q minus omega t times the real part of that. This is 1 over q minus omega squared cos omega t. That is a YP that works for this example. Which should make sense if you think about it. I mean, initially I said, well, you could guess a linear combination of cosine and sine here for the YP without thinking about complexification. And if you think about it, the sine for this kind of problem at least would be kind of irrelevant because it's a cosine over there. You don't have a first derivative, so there's, when you plug in just a cosine into the left-hand side, you're not going to get a sine involved because there's no first derivative. You only have to guess something involving cosine because there's no y prime in here. All right, let's keep going with this example. Guess I'll go ahead and erase this part right here. Let's add some initial conditions. We can write down the general solution of the original forced equation. Gen solution of forced equation, the original one, the real one. Y equals YH plus YP, K1 cos square root of QT plus K2 sine square root of QT plus 1 over Q minus omega squared cos omega t. Let's consider an initial value problem where y of 0 and y prime of 0 are both 0. The mass isn't moving and it's at its equilibrium point at the very beginning when you start tipping the table back and forth. So it is going to move. And the origin is no longer an equilibrium point because of the forcing. Is there an equilibrium point? Could it possibly stay still as you tip the table back and forth? I don't know at the moment. Doesn't sound like it would be possible. These initial conditions are also nice in terms of solving for K1 and K2. Let's see. Y prime, fit it in here. Differentiate that. It's going to be negative square root of Q K1 sine square root of QT with the chain rule plus square root of Q cos. Forgot my K2. Square root of Q K2 cos square root of QT minus, differentiate that, omega over Q minus omega squared sine omega t. Plug in t equals 0 into both equations, set the results equal to 0 in both. What kind of system will we get? Put it up here with the first one. The sine of 0 is 0, so that goes away. Cosine of 0 is 1, so you get a K1 and a 1 minus Q omega, a 1 over Q minus omega squared. 0 equals K1 plus 1 over Q minus omega squared. That's nice. That means K1 itself is 1 over omega squared minus Q, if you like, or negative 1 over Q minus omega squared, either way. And with the second equation, two terms go away. The two terms involving sine And actually, because cosine of 0 is 1, you'll end up with k2 equaling 0. Does that make sense? See, when you set this equal to 0, after plugging in t equals 0, these two terms are going to go away. This one, cosine 0 is 1, you'll get square root of q times k2, but that's going to equal 0 because I'm setting the initial velocity equal to 0, therefore k2 must be 0. So with those initial conditions, we can say the unique solution of the IVP with those initial conditions is y equals, can actually factor out a 1 over q minus omega squared because I have it with the k1 going right there. That's 0. I've got it next to the y, it's part of the yp. So it can be factored out. 1 over q minus omega squared. With the yp, it's a positive coefficient of the cosine. With this part, it's a negative coefficient. So if I'm careful about signs, I'll get cos omega t minus cos square root of qt. Q and omega are fixed. This is the answer in terms of q and omega. In your problems, you'll have particular q's and particular omegas. But it's worth thinking about this general case, and we're going to go back to Mathematica now and look at the plot of this thing. And we're going to see something pretty interesting. This plot that we make, plot of this function inside of manipulate, is going to be pretty cool. Especially for certain values of q and omega. Square root of the palette here. Oh, what interval should I pick? I don't know. Let's try 100 actually. I'm going to vary q and omega. I can plot range vertically. Let's give ourselves flexibility. Let's go -5 to 5. It's possible this thing could be large if q is close to square root of omega. Excuse me, omega is close to square root of q. What should I start q at? Maybe at a perfect square like 9. Let it go down to 1, and maybe as high as 25. I'm actually going to start omega relatively large, representing a small, I'll start at small. Sorry about that. I'll start at small. Say close to 1, and let it go up to maybe 20. So omega being small corresponds to an external frequency for the forcing function that's relatively small. Small frequency means large period. So that's a slow wave oscillation in the forcing function. As omega gets bigger, that's a bigger frequency, which is a smaller period. It's a faster oscillation in the forcing function. It's already pretty interesting. Can you see that graph? It is there. Let's increase omega. See what happens to the graph. Oh, I need a plot style performance goal quality, it looks like. I let it go, it's smoother. amplitude's getting bigger, and look at that. What in the world? That's pretty cool, don't you think? What's happening? Why is that happening? Whoa! What's happening? Look at the values of omega and q. Omega is very close to the square root of q, which is a case we had to exclude. We said omega is not equal to square root of q when we wrote this formula. I should write it again to emphasize that. Omega is not equal to square root of q, or plus or minus square root of q if you allow negative omegas, although we typically think about positive omegas. We're not in that case, but we're close to that case over here. And what's happening? The function is blowing up. The mass on the spring is going back and forth with a bigger and bigger amplitude until it breaks. The forcing frequency is close to the natural frequency of the harmonic oscillator. Omega is the angular frequency of the forcing function. Square root of q is the angular frequency of the harmonic oscillator itself. That's related to what kind of spring you have. The spring itself and its restoring force from Hooke's law is related to q, as well as the mass itself. And that sets up a natural frequency in the absence of the forcing function. As an angular frequency, it would be square root of q. As a regular frequency in hertz, it would be square root of q over 2 pi, in times and seconds. If the forcing function, if the external forcing function has a frequency that's very close to the forcing function, the natural frequency of the oscillator itself, that causes the oscillations to increase in amplitude when you don't have any damping, or maybe if the damping is really small. And it's going to cause the spring to break, which should intuitively make sense if you somehow are able to oscillate your table in a certain way. It should make some intuitive sense that perhaps you can get the amplitude to get bigger and bigger. It will cause the spring to break, or cause the glass to shatter if you sing at a certain frequency. Think of a goblet as being like a harmonic oscillator responding to an external forcing function that's sound waves of a certain frequency. And if that frequency of the sound waves is close enough to the natural frequency of the goblet, it could cause it to shatter. Maybe that's what's happening. It's the oscillations of the glass. More fun with complex numbers to finish off class today. Turns out, okay, I want to keep that, that if we somehow complexify this equation, it can be beneficial for us in terms of trying to understand why the graph looks the way it does. What you're seeing here is kind of what's called a beating phenomenon. And this will happen maybe to physics, and you've got two tuning forks such that when you hit them, their frequencies are pretty close together. And you get the sounds combining to get sort of a beating phenomenon. It's loud, then it's soft, then it's loud, then it's soft. Anybody seen that in physics? I showed that to you?
Heard it.
Heard it? Yeah. That's what we're seeing here with these graphs. How can you understand, there's sort of like two frequencies. The frequency of the fast oscillations and the frequency of sort of the slow oscillation, the overall waves, if you think of it as one wave. I mean, it's sort of like two enveloped waves. One wave like here, and one wave down there. Those have periods and frequencies too. Can we figure out what they are? The answer is yes. And a nice way to do it, it turns out, is with complex numbers, although what I'm about to do is pretty tricky. I'm going to call this A, after all it does equal A. Looks like I erased it. The A from the YC. Call that A to keep things simple. This is the real part of A times e to the I omega t minus e to the I square root of q t. This function here. That should make sense if you think about Euler's formula. This is going to be cos omega t plus I sine omega t. This, without the minus sign, is going to be cos square root of qt plus I sine of square root of qt. You are subtracting it. The real part of that involves just the cosines, not the sines. This thing up here, the A is a real number, so that just stays as it is. This thing up here is the real part of that function. I'm going to use a little trick now to rewrite that function. I'm going to let alpha equal omega plus square root of q over 2 and beta equal omega minus square root of q over 2. Those two expressions have a couple nice properties. If you add them, you get omega. Think about that. The square root of q parts cancel. You get omega over 2 plus omega over 2 is omega. And if you subtract them, alpha minus beta, the omega parts cancel, and the negative sign cancels to get a positive sign. You get square root of q over 2 plus square root of q over 2, which is square root of q. So making those substitutions results in these equations, which allows us to replace the omega and the square root of q in these expressions. I'll keep the RE there. Like this. Omega is alpha plus beta. I'm going to multiply it by t as well. I get e to the I omega t becoming e to the I alpha t plus beta t, because omega is alpha plus beta. And since square root of q is alpha minus beta, I can replace the square root of q with alpha minus beta, multiply the t through and get that. What's the benefit of this? Well, by properties of exponents that work with complex numbers. This is e to the I alpha t times e to the I beta t. And this thing right here is e to the I alpha t times e to the negative I beta t. There's a common factor of e to the I alpha t that can be factored out. Like this. And it turns out what's left inside the parentheses here can be simplified, once again using Euler's formula. There, I tried it in my head. You'll get a, let's think about the cosine and sine individually. You'll get a cosine beta t from that one, and a minus cosine negative beta t from this one. Cosine is an even function, so cosine negative beta t is the same as cosine beta t. So you get cos beta t minus cos beta t. The cosines cancel. What about the sine term? You get an I sine beta t from this one minus I sine negative beta t. Thinking about Euler's formula here, you might want to write this out on your own after class. Time over time. Let me just try to finish here quick. Sine is an odd function, so sine of negative beta t is negative sine of beta t. The two negative signs cancel to give you plus, so you have really 2I sine beta t. This simplifies to 2I sine beta t, which can now be multiplied by this, which is cos alpha t plus I sine alpha t. And you can ultimately take the real part of it. Amount of time, the goal in this is to help us figure out the frequency and period of the fast oscillations and the slow oscillations. I'm almost there, but I've run out of time. I would encourage you to study section 4.2, especially page, well, actually it's 4.3, especially page 418. Go ahead to page 418 and study the book's example of this. I will finish it off on Wednesday. See you then.